Hi, this is Mr. Allen. This is another edition of Admiral Science. And today we're going to be talking about electrons and chemical bonds. And we're going to find out why electrons and chemical bonds are so important, what their relationship is, what does it tell us about chemical bonds, how does the electrons play a factor into it. And we're going to start off with what we should know. We should already know much about the organization or the arrangement of the periodic table. We know that for one, the periodic table goes from 1 to 118 elements now. And we know that they're arranged by the atomic number, for one. So 1 starts right here, and the last atomic number is down here. And we know that the atomic number tells us the number of protons. We know proton number never changes. All right, because if you change the proton number, you change the element. And so we do not change the proton number with the element. But we also should know that the periodic table is organized into groups. And there are 18 total groups. Group 1, Group 2, Group 3, Group 4, Group 5, Group 6, Group 7, Group 8, Group 9, Group 10, Group 11, Group 12, Group 13, Group 14, Group 15, Group 16, Group 17, and Group 18. And why these groups are so important is because not only do these groups, we organize, all the elements in this group react pretty much the same. All the elements in every group react the same. And we know that groups are the rows of the periodic table, the columns of the periodic table. And all the elements in group 1 react similarly. All the elements in group 2 react similarly. All the elements in group 13 react similarly, 14, 15, 16, 17, 18. All right. And the reason why they react similarly is because of their valence electrons. And if we can remember, valence electrons are the electrons on the outermost energy level. For example, all the elements in group 1 have 1 valence electron. All the elements in group 2 have 2 valence electrons. All the elements in group 3 have 3 valence electrons. All the elements in group 4 have 4. All the elements in group 5 have 5. All the elements in group 6 have 6. Group 7, this is 13, group 14, group 15, group 16, group 17, group 18. Now, as you saw me doing earlier, the groups for the double digits, you look at the second digit. So all the elements in group 13 have 3. All the elements in group 14 have 4. All the elements in group 15 have 5. All the elements in group 16 have 6. All the elements in group 17 have 7. And all the elements in group 18 have 8. All right, so these are our groups. All right, and the valence electron are the electrons on the outermost energy level. And when you hear me say orbits, that's the same thing as energy levels. All right, and these elements here all have 1 valence electron. So if we look at hydrogen, which is our first element, and we know that hydrogen has 1 proton. And we know that hydrogen is the only element naturally occurring that has no neutrons. But then we talk about the electron on the outermost energy level. So because hydrogen only has 1 electron, this is its valence electron, and it's the only electron, valence electron. It's the electron on the outermost energy level, and because it only has 1 level, then it has 1 valence electron. Helium, on the other hand, although it's on 1 level, has 2 valence electrons, and that's it for helium. All right, helium is the exception to the rule of 18. Although these ones right here, they have 8 valence electrons. Helium, because it only has 2 electrons total, it has 2 valence electrons for helium. It is the exception to the rule of 8. But it is still complete. Just like the others, helium is just like the others in group 18, it has a complete outermost energy level. It has a complete orbit. All right, because remember that first orbit here can hold a maximum of 2 electrons. Then the second orbit can hold, so the first orbit can hold a maximum of 2 electrons. The second orbit can hold 8. The third orbit can hold 8. The fourth orbit is 18. And if we have to, the fifth orbit is also 18. So 2, 8, 8, 18, 18, then it goes 32, 32, so on and so forth. All right. So this is the total. This is the groups, and groups are very important as in it tells us the number of valence electrons, and valence electrons are the important part of chemical bonding. Now periods tell us the number of energy levels or the number of orbits. So we have 1, 2, 3, 4, 5, 6, 7. All right. So all the elements in period 1, which is 2 elements in period 1, have 1 orbit or 1 energy level. And remember, orbit is the same thing as energy level. All right. So all the elements in period 2 have 2 energy levels. All the elements in period 3 have 3 energy levels. All the elements in period 4 have 4 energy levels. All the elements in period 5 have 5 energy levels. All the elements in period 6 have 6 energy levels. And all the periods in element 7 have 7 energy levels. And remember that these two are a part of group 6, period 6 and period 7. Alright, so we're arranged in periods, we're arranged in groups or families, and they each tell us something different. Remember, groups tell us the number of valence electrons, and periods tell us the number of energy levels. And we should lastly know valence electrons. Now, valence electrons are the electrons on the last energy level. I don't know why that streak keeps coming up, but last energy level. These are the valence electrons. So however many levels the element has, the electrons on the last energy level are the valence electrons. Alright? So for example, this lithium is in group 1. Beryllium, group 2. Boron is in group 13. And remember, we look at the second digit. Carbon is in group 14. Nitrogen is in group 15. Oxygen is in group 16. Fluorine is in group 17. And neon is in group 18. And we look at the last energy level. The last digit for the valence electron. So if you do your models and they come up with 3 for the groups in 13 or 4 in the groups in 14, you're doing it correctly. Alright, so remember, in general, the number of valence electrons of a representative element is equal to the group number, and remember the double digits are the second digit. You look at the second digit for the valence electron number. Alright, so why are valence electrons important? Valence electrons determine if an atom of an element was bound with different atoms. Alright, so depending on the number of valence electrons, and look at lithium. Lithium has 1 valence electron. So if you have the nucleus right here for lithium, and then you got the energy levels 1, 2. Remember, lithium's in period 2, so it has 2 energy levels. 1, 2. Lithium's in group 1, so it has 1 valence electron. And here's our 1 valence electron. Fluorine, also in period 2. So it has 2 energy levels, 1, 2. But fluorine is in group 17, and so it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And that's the number of valence electrons. Alright, so now we get to Lewis dot structures. And the reason why we do Lewis dot structures, we're going to discuss. Remember, there are a couple of things. First, our modern structure of an atom is the electron cloud. The only issue with electron cloud model, I can't write up there. The only issue with electron cloud model is that it shows us the general look of what an electron looks like. It shows us that electrons are in a cloud around the nucleus. But the only thing it does not show us directly is the number of electrons. And the number of electrons, especially the valence electrons, are the important part of chemical bonding. So when we look at if elements chemically bond, we use the model right before it, which is the Bohr model. And the flaw with the Bohr model is it does not tell us the general location of electrons because it puts them in fixed paths, and we know now that electrons don't belong in fixed paths. but the Bohr model does tell us the number of electrons, and it does show us how elements chemically bond with other elements using valence electrons. So Bohr model shows us things that electron cloud model cannot, even though this is the accepted theory. Alright, but to make life easier, they came up with the Lewis dot structure. And the Lewis dot structure helps us identify easier the valence electrons. And so that way we don't have to make these large structures, because if we did the valence for fluorine, we have fluorine here, we got to put our 9 protons because it has an atomic number of 9, our 10 neutrons for its atomic mass, and then we have to write out these structures. 1, 2, we gotta make our next level. 1, 2, 3, 4, 5, 6, 7. And instead of doing this twice or however many times we need to make a fluorine molecule, instead of doing this, and because remember this part of the element won't change, alright, and the second level, because it's not really being touched, it's complete, that part won't change. And I'm sorry if it's the same color, but the inner part of this element won't change. The only thing that's going to change is the valence electrons. And so because we only need to work with valence electrons with chemical bonds, that's all we need to focus on. So they came up with the Lewis dot structure, and the Lewis dot structure just works with the valence electron. And what it shows is the valence electrons around an element. So let's look. When making a Lewis dot structure, you plot the valence electrons around the atomic symbol of the element. So for example, they just have, let me erase this. And it won't let me erase. Alright, erase all things on this slide. And because we are, when we're working with fluorine, we're just in fluorine, so I'm going to make fluorine. Alright, fluorine we know has an atomic number of 9, and based off its group, we know it's in group 17. And so remember, when we look at valence electrons, we look at that second digit for double digits, and so we should have 7 valence electrons. So here's how you do it. You go 1, 2, 3, 4, 5, 6, 7. Alright? So this is how you will make a Lewis dot structure, because if you only look at the valence electron, we're dealing with 7 valence electrons. Alright? So you plot your valence electrons around the chemical symbol. So the chemical symbol of fluorine is F. And we then plot our 7 valence electrons. Again, if you don't know how we got valence electrons, we use this second digit of the group number. Alright? So the purpose of elements in chemical bonds is to complete their outermost energy level. So remember how our periods had 1, 2, 3, 4, 5, 6, 7. They let us know the number of periods we have. Well, whatever that number is, you want that layer to be complete. Alright? So if you're talking about period 2 that has 2 energy levels, you want that second energy level to be complete. And the octet rule, and if we cannot remember, alright, so we have 1. Our first energy level, if they only have 1 energy level, that means they have a maximum of 2 electrons. And we know that there are only 2 elements with 1 energy level, that's hydrogen and helium, because they're in period 1. They're the only 2 elements in period 1. Alright? So they have 2 electrons total. Alright? Those on the second energy level, they have 8 electrons total. That's the maximum for their energy level. Alright, the third level also is 8 electrons. And they want to complete their energy level as well. The fourth level is 18. And to my knowledge, we do not deal with anything larger than 3 in 8th grade science. But if, case in point, the fourth energy level is 4. The fifth is the fourth is 18. The fifth is also 18. 6 is 32, and 7 is 32. That's if we need it, but we don't work that far in 8th grade science. So the last level, so the octet rule says that elements want to be complete. All right, everybody likes to feel complete, and they want to be complete on their last energy level. So the elements that we're working with typically will be complete with 8 or 2. All right, so whether in 2 or 3, in row 2 or 3, or 18 for elements on the 4th level, but typically 8 is the number they look for. And for potassium and calcium, which we'll be dealing with, they're looking for 18. So, and I do apologize for that. That's let's construct the Lewis dot structure for calcium. So calcium has an octet rule of 8, just like everyone else. You want 8. That's the golden number. You want 8 on the last level. So calcium. Let's see. When we construct our calcium element, you start here. 1, 2, 3, 4. Oh, that is incorrect. Let's erase that. Because what group is calcium in? Let's see. If we are correct, our group for calcium is what? Group 2. So that means it has how many valence electrons? 1, 2. Alright. So that means it has spaces for 1, 2, 3, 4, 5, 6. It can bond 6 times with different elements. Alright. So, but this is the Lewis dot structure. So 1 and 2. And these empty spaces, because of the octet rule of 8, these empty spaces are for other elements to bond with calcium. So, okay, now based on our Lewis dot structure of the following, which would be a perfect match for calcium? So let's see. Remember, we want that magic number of 8, and we want to know which of these elements is going to give it the magic number of 8. All right, so beryllium is in group 2 as well. So let's see, 1, 2. Oxygen is in group 6. So let's look at it. 1, 2, 3, 4, 5, 6. So oxygen is looking for someone with 2. You might have a match there. All right, let's look at carbon. All right, we do it, and carbon is in group 4. So 1, 2, 3, 4. And chlorine is in, let me get this correct, group 7. So if we look at it, 1, 2, 3, 4, 5, 6, 7. So if we go back and look at our calcium, it has 6 spaces, so it's looking for a match for them 6 spaces. Which one of our elements up here will be a perfect match for oxygen? I gave you guys the answer. The correct answer, if you said it, is oxygen. All right, because oxygen has 6 valence electrons, which means it has 2 extra spots, and calcium has 2 valence electrons with 6 extra spots. So these two will be a perfect match, and so you'll show a bond with calcium to, and I'm going in a particular order for this one, but typically you go around in the circle before you complete, and oxygen, which is 1, 2, 3, 4, 5, 6, and these two will share 7 and 8. Alright, and instead of writing it that way, you can also write it this way, because you would not have to, it's understood that if you do not write the dots and you just draw it this way, that these areas around them are already matched up or complete, and this shows basically this relationship here. Alright, so that line is the same thing as 2 dots. Alright, so now let's try to create a Lewis dot structure with water. Alright, so here we have 1 for that one, 1 for this one, and oxygen has a total of 6. So it's missing 2 spaces. So here's how we would do it. They will match up here and here, or to show a different color so that we can see who the arrangements. So let's say we give hydrogen 1 dot, a red dot, give that hydrogen a red dot. I'm going to change my ink color up some, and I'm going to give oxygen blue dots. 2, 3, 4, 5, 6. Alright, so here's how the arrangement will look. 1, 2, 3, 4, 5, 6. And alright, so we have them sharing these, and that way their octet rule is complete. And remember that hydrogen completes itself with it when it has 2 electrons. Alright. Alright, and that was the Lewis dot structures and valence electrons. If you have any questions, please check back for the next episode of Admiral Science. And I'll be looking for volunteers to participate in next week's Admiral Science videos. So up next is going to be ionic and covalent bonds, and then we get into the naming of the bonds. But today, just to recap, it was to give you an idea of the Lewis dot structure, valence electrons, and if it bonds or what can it bond with. Alright, we're going to be working with more bonding and more of the Lewis dot structure in class, but this is just a brief synopsis of valence electrons and its importance into chemical bonding. Alright, look forward to seeing you next time on Admiral Science. Thank you.